Hey everybody, for today's video, we're going to look at some cracks in the Earth that are so large and so deep they can be seen from space. Here's 15 Earth cracks that are visible from above. Starting with number 15, the tectonic fissure of Þingvellir. The Þingvellir National Park in southwestern Iceland is home to one of the most visible tectonic cracks on the surface of the Earth, the rift between the North American and Eurasian tectonic plates. This geological feature marks the boundary where the two continental plates are slowly drifting apart. Now, the movement of these plates, it averages about 2.5 centimeters per year, as part of the mid-Atlantic ridge that runs through Iceland. The resulting rift valley, which is a few kilometers wide, is one of the few places in the world where such plate boundaries are visible above sea level. The rift is composed of dramatic cliffs with clear visual evidence of tectonic divergence that's happened over the thousands of years. The most prominent crack is more than 7.5 kilometers long and reaches depths of up to 64 meters in some areas. Other nearby fissures contribute to the area's network of visible splits in the Earth's crust. These cracks are not only visible on foot, but they're also clearly detectable in satellite images due to their dark linear contrasts and their shadowing effects on the landscape. The movement of the tectonic plates here has led to repeated earthquakes and the gradual reshaping of the terrain. In some locations, small-scale sinking of the land and uplift events have become documented, shaping the contours of the rift valley. These surrounding areas includes lava fields, cracks filled with groundwater, and visible separation zones where past volcanic eruptions have happened. But despite its violent geological history, this area has been continuously occupied since the Viking era, and it's also notable for being the site of the world's oldest parliament, established in the year 930 CE. Today, this zone remains a popular tourist attraction, not only because of its historical importance, but because of its striking geology. In addition to walking through the rift, you can also snorkel or dive here in the Sulphur Rift. That's a water-filled crack with some of the clearest natural water in the world. But from satellite views, the fissure zone appears as a linear scar across an otherwise barren, moss-covered volcanic plain. The cracks in the fault zones are enhanced by Iceland's minimal vegetation and glacial erosion. Þingvellir remains a textbook example of continental rifting, clearly demonstrating the mechanics of plate tectonics to scientists and observers like us. Number 14, the Dabahu Fissure in Ethiopia. In 2005, a massive geological event happened in a remote, afar region of northeastern Ethiopia, producing one of the most significant cracks in the Earth visible from space in the 21st century. It's known as the Dabahu Fissure. This rupture appeared over the course of just a few days during a period of intense seismic activity. The initial crack was more than 60 kilometers long and in places several meters wide. It formed when underground magma pushed its way to the surface, causing the Earth's crust to split open rapidly. The Afar Depression lies at the junction of three tectonic plates, the African, Arabian, and Somali plates. It is one of the most volcanically active and unstable places on Earth. This fissure marked the beginning of a larger tectonic event where the Earth's crust is in the process of being pulled apart, eventually leading to the formation of a new ocean. This phenomenon is happening on a timescale of millions of years, though, but the sudden formation of such a large crack offered scientists a rare chance to observe the early stages of continental breakup in real time. The fissure formed after a swarm of over 160 earthquakes shook the region, culminating in a volcanic eruption from the Dabahu volcano. Instead of a traditional cone eruption, though, the magma moved sideways underground, forcing its way between the layers of crust and causing the land to split. The result was a dramatic scar that's clearly visible in satellite imagery, and researchers from around the world have studied the event closely, using radar interferometry and satellite photography to monitor changes in the landscape. These tools have shown continued deformation in the region over the years since the initial fissure appeared, and cracks continue to grow and new faults have formed. This fissure is a key part of the broader rift system that could eventually separate the Horn of Africa from the rest of the continent. But from above, it looks like a clean dark line that stretches across an otherwise flat and arid terrain. It intersects with older cracks, and it creates a complex pattern of geological activity that tells the story of a land in flux. It serves as a real-time laboratory for understanding how continents break apart and how new ocean basins begin to form, offering some insight into one of the most fundamental processes on Earth. Number 13. The Earth Cracks of the Badwater Basin in Death Valley, California. Death Valley's Badwater Basin. It's not just the lowest point in North America, at 282 feet, that's 86 meters, below sea level. It's also home to an array of surface fissures and crustal fractures that are visible from space. These aren't traditional tectonic rift valleys like those in Iceland or East Africa, but rather surface-level cracks caused by a mix of salt deposition, tectonic tension, and extreme climate. The Badwater Basin lies within the Basin and Range Province. This is a huge region in the western United States, and it's characterized by a series of roughly parallel mountain ranges and desert valleys. This entire area has been subjected to crustal extension for millions of years, pulling the land apart and forming a patchwork of fault lines. The normal faulting in the region is responsible for the valley's extreme topography, and in Badwater Basin, this stretching is compounded by the deposition of salt from evaporated ancient lakes, which leaves behind large salt flats and polygonal fracture patterns. During some dry periods, the salt crust undergoes thermal expansion and contraction, which forms cracks that resemble a network of white scars. These salt polygons are typically a few meters in diameter, but larger fissures have also been observed in satellite images, running across the flats and intersecting with fault lines at the basin's edge. The low vegetation here and the bright surface albedo of the salt makes these fissures stand out in aerial photographs, especially in high-resolution imagery. Beneath the visible surface, though, Death Valley does also have some fault lines, including the Furnace Creek fault line system and the Southern Death Valley Fault. These contribute to occasional seismic activity and gradual deformation of the valley floor. While the valley's overall tectonic activity is slower than in places like the East African Rift, it is ongoing and measurable. This slow rifting and associated land subsidence contribute to long-term instability in the salt crust and the formation of additional cracking. Although visible cracks at Badwater Basin are not massive canyon-like splits, they are nonetheless prominent enough to be mapped and monitored by satellites. Their highly regular and angular shapes also attract some attention from photographers and geologists, of course, as they resemble man-made geometric patterns. So, as such, the Badwater cracks serve as a surface-level record of both geologic and climatic forces, clearly visible, even in moderate-resolution orbital imagery. Number 12. The Jidatan Earth Fissure, Tibet Plateau in China. In the high-altitude region of the Qinghai-Tibet Plateau lies the Jidatan Earth Fissure, one of China's most prominent examples of active surface cracking caused by tectonic and cryogenic, that's freeze-thaw cycle process. This fissure is located in the Kunlun Fault Zone. Now, this is an active tectonic region that marks the northern boundary of the plateau, where the Indian and Eurasian plates converge. The Jidatan area has experienced a significant number of earthquakes, and the resulting stress on the crust has led to long, deep cracks. Now, the zone was brought to international attention after the 2001 Kunlun earthquake, which had a magnitude of 7.8, and that event triggered some dramatic surface ruptures over a 400-kilometer stretch. Some of the fissures that formed were up to 2 meters wide and several kilometers long. These cracks cut across roads, they altered water flow patterns, and created displacement zones that remained visible decades later. Geologists studying the fissures here use tools like synthetic aperture radar and GPS networks to monitor the movement and expansion of the cracks. The data helps researchers understand how stress is transferred across the Tibetan Plateau and how major fault systems like the Kunlun Fault evolve over time. The location does also offer insights into how tectonics interact with climate-driven geological process at high altitudes. But from a satellite perspective, the fissure is most notable after snowfall or rainfall, when the moisture darkens the cracks and enhances the contrast. The fissures tend to follow linear paths reflecting the alignment of fault traces beneath the surface. Though the region is remote and sparsely populated, this activity is globally significant due to the scale of the tectonic forces involved. The fissures here are not just passive scars, they're part of an active and evolving tectonic landscape that continues to form the Earth's surface. This makes it a crucial case study in both earthquake science and climate geology interactions, visible even to orbiting satellites tracking the shifting crust. Number 11. The San Andreas Fault, California. The San Andreas Fault. It's one of the most famous and one of the most studied and one of the most visible fault lines in the world. stretches about 1,200 kilometers, that's 750 miles through the state of California, and it marks the boundary between the Pacific and North American plates. It's a transform fault, meaning the two tectonic plates slide past each other horizontally. Now, this ongoing motion, at a rate of roughly 30 to 50 millimeters per year, creates a massive linear scar across the California landscape, visible both on the ground and from orbit. From the Gulf of California in the south to Cape Mendocino in the north, the San Andreas Fault runs through a wide variety of terrains, from desert basins to mountain ranges and agricultural valleys. In Southern California, it is particularly visible in areas like the Carrizo Plain National Monument, where the fault cuts a remarkably straight line across grassland and hills. And this section includes features like offset stream channels, sag ponds, and pressure ridges that demonstrate the horizontal motion of the plates. In satellite images, the fault often appears as a dark linear groove or a subtle color contrast following a straight or gently curving path through the terrain. The most famous and destructive earthquakes in Californian history have happened along this fault system, including the 1906 San Francisco earthquake. That event caused a surface rupture of over 470 kilometers, that's 296 miles, and it permanently offset fences, roads, and entire sections of terrain by as much as 6 meters. Even in the absence of a recent quake, the San Andreas Fault is a site of continuous geological deformation. Subtle changes in elevation and horizontal movement are monitored using satellite radar and GPS, which have revealed slow, creeping shifts along certain segments. The fault zone is divided into three main sections: the northern, the central, and the southern segments. The central section near Parkfield is known for small, frequent quakes and aseismic creep, while the southern section running near the Salton Sea is overdue for a major rupture, according to geologists. Because this segment hasn't produced a significant quake in more than 300 years, it's under intense observation. But from space, the San Andreas Fault stands out, due to the dramatic difference in landforms and vegetation patterns on either side of the fault. Satellite imaging, especially during early morning or late afternoon passes, reveals long, continuous shadows along the fault scarps and clear topographic displacements that trace the path. It's a visible expression of a continental scale plate motion. The San Andreas Fault remains one of the clearest examples of a large crack that defines a major geologic boundary, and its activity continues to shape the landscape of California. Number 10. The North Anatolian Fault in Turkey. The North Anatolian Fault, it's one of the most active strike-slip fault systems in the world, rivaling the San Andreas in both scale and seismic potential. It runs roughly 1,500 kilometers or 930 miles across northern Turkey, from the Aegean Sea in the west to the eastern edge of the country near the border with Armenia. The fault marks the boundary between the Anatolian Plate and the Eurasian Plate, and it's responsible for some of the most destructive earthquakes in the region's history. The fault is a right lateral strike-slip system, meaning that land on either side of the fault moves horizontally in opposite directions. Over the last century, a sequence of major quakes has ruptured almost the entire length of the fault from east to west, creating long linear fractures that are visible from above. These ruptures have left behind traceable lines of surface deformation that cut across valleys, rivers, roads, and even cities. Notably, the 1999 Izmit earthquake, which struck the industrial city, it caused a rupture of 150 kilometers in length. This event alone displaced the ground by more than 5 meters in some areas, and it was captured in high-resolution imagery. The scar from this quake remains highly visible in satellite photographs, showing a zigzagging fracture line through farmland, urban areas, and the coast of the Sea of Marmara. In some places, the fault creates long, narrow valleys known as fault troughs, while in others it produces offset ridges and linear lakes, like Lake Ladik and Lake Sapnaka. These geomorphological features make the fault line visible to orbiting satellites even without recent seismic activity. Differences in vegetation, soil moisture, and erosion patterns further show its visibility in multispectral satellite imaging. The segment of the fault closest to Istanbul, near the sea, is a point of high seismic concern. It's the only section of the fault that has not ruptured in the recent century-long sequence of quakes, making it a likely location for a future major quake. Satellite monitoring and GPS arrays have confirmed accumulating strain in this section. Modeling shows a high probability of a rupture here in the coming decades. From space, the North Anatolian Fault appears as a long, jagged scar. In some areas, the line is straight and uninterrupted for dozens of kilometers. In others, it winds through mountain passes and valleys, yet its presence is always detectable due to the sharp contrast between the landforms on either side. It's a classic example of a large earth crack caused by continental plate movement, and one of the most significant fault lines visible on Earth today. Number 9. The East African Rift System, Ethiopia to Mozambique. The East African Rift System, or EARS, is one of the largest and most visible continental rift zones on the planet. It stretches over 3,000 kilometers from the Afar Triangle in northeastern Ethiopia through Kenya, Tanzania, and Malawi down to central Mozambique. It marks the location where the African plate is slowly splitting apart into two separate plates, the Nubian plate to the west and the Somali plate to the east. This process is active and ongoing, and the resulting fractures, valleys, and fissures are clearly visible from space. Unlike localized fault zones, the East African Rift is a system of interconnected faults, grabens, and fissures that collectively form a massive scar that runs down the spine of eastern Africa. The rift has been forming for the past 25 to 30 million years, and evidence suggests that the process may eventually lead to the creation of a new ocean basin separating parts of eastern Africa from the continent's interior. In Ethiopia's Afar region, the rift manifests in a highly visible series of depressions and parallel fault blocks, and some of the deepest and widest cracks here are found, including sections where the ground is pulled apart by several meters. Volcanic activity is intense in this region, with fissure-fed eruptions and magma intrusions that form new landforms and enlarge existing cracks. In 2005, the Dabahu fissure, which was part of this rift system, opened suddenly, and it added more than 60 kilometers of visible surface fracture to the growing scar. Farther south in Kenya and Tanzania, the rift becomes a series of deep valleys flanked by high escarpments and dotted with fault-formed lakes like Lake Turkana. These lakes occupy grabens, or down-dropped blocks of crust, bounded by steep faults. This lineation of geometry of these faults is clearly visible in satellite imagery, with the entire regions showing step-like terrain and fracture zones. In satellite photographs, the rift appears as a dark linear depression that's punctuated by crater lakes, volcanic cones, and straight escarpments that mark the fault boundaries. High-resolution radar and optical satellite data continue to track the deformation across the system, and it reveals some active widening and crustal thinning. This whole fault system in East Africa is more than just a crack. It is a dynamic and evolving boundary where a continent is being pulled apart. The massive scale, the linearity, and the motion make it one of the most prominent and scientifically important surface ruptures on Earth, and is fully visible from orbit. Number 8. The Denali Fault in Alaska. The Denali Fault in Alaska is a major intracontinental strike-slip fault system that runs for over 1,200 kilometers, about 750 miles, through the southern interior of the state. It's part of a broader network of faults that accommodate the motion between the Pacific and the North American plates. The fault gained international attention in 2002 when it produced a magnitude 7.9 quake, one of the largest recorded in the United States, and it left behind a massive surface rupture that remains visible from the air and through satellite imagery. The Denali Fault is similar in type to the Californian San Andreas Fault. Both are right lateral strike-slip systems, meaning that the land on either side of the fault moves horizontally in opposite directions. But what sets this one apart is the remote mountainous setting and the extent of its unmodified fault trace. These are large portions of the fault that run through the wilderness and national park lands, allowing the rupture scars to remain exposed and undeveloped. The 2002 quake caused a surface rupture of nearly 340 kilometers in length, and in some areas the ground shifted by up to 9 meters horizontally, leaving behind sharp breaks in the landscape. Entire ridges, forests, and glacial moraines were split, with features like stream channels and dirt roads visibly offset. One dramatic result was the offset of the Trans-Alaska Pipeline, which had been especially engineered to withstand seismic movement and survived the event with only minor damage. From space, though, this trace is highly visible, especially in the Alaska Range where the surrounding snow and rock contrast with the fault scar. The 2002 rupture is especially clear when it crosses open tundra and gravel plains. The Denali Fault continues to accumulate stress, and it remains an active seismic hazard. It is monitored using a combination of ground-based GPS, seismometers, and remote sensing tools such as INSAR, that's synthetic aperture radar, and these tools have detected small but measurable creep and deformation since the 2002 event, especially in segments near the Tok and Tachunda faults, which are considered possible rupture sites in the future. But what makes the Denali Fault especially notable is the combination of size, isolation, and preserved surface rupture. Its visibility from orbit and its role as one of the most significant seismic events in recent U.S. history make the Denali Fault one of the largest and clearest earth cracks in the Northern Hemisphere. Moving on to number 7, the Western Ghats Escarpment Fault in southwestern India. The Western Ghats Escarpment, which runs along the southwestern margin of the Indian subcontinent, is one of the most prominent tectonic boundaries in South Asia. Yet it's often viewed primarily as a mountain range rather than a massive fossil tectonic crack that it truly is. This escarpment marks the ancient rift edge of the Indian plate, formed during the breakup of the Gondwana supercontinent around 100 to 130 million years ago. Though long considered geologically inactive in terms of seismic hazard, the escarpment's size, linearity, and preserved fault structure make it one of the most visually striking cracks visible from space. It stretches more than 1,600 kilometers from Gujarat in the north to Kerala and Tamil Nadu in the south. The escarpment rises abruptly from the western coastal plains and creating an elevation gain of about 1,200 meters in places, within just a few kilometers of horizontal distance. The origin of the Western Ghats Escarpment is tied to a rifting event, as the Indian plate separated and drifted northwards towards its eventual collision with Eurasia. The crust fractured and tilted downward towards this newly forming ocean basin, what is now the Arabian Sea. This created a faulted continental margin, similar to modern-day examples like the East African Rift, except this one's no longer active. The faulting produced a steep scarp face we see today, which separates the lower elevation Konkan and Malabar coasts from the highlands of the Plateau interior. From a satellite perspective, the escarpment is unmistakable. In Google Earth, Sentinel-2 and NASA's MODIS imagery, the Ghats appear as a bold, continuous wall of uplifted terrain. It casts long, strong shadows when viewed during low sun angles, and in places like Nilgiri Hills, the land drops dramatically from the rugged plateau to the coastal plains, which shows the vertical displacement along the faulted boundary. Despite the inactive status, though, the escarpment is not entirely without motion. GPS data and INSAR analysis suggest minor flexing and slow uplift in some sections, likely due to isostatic readjustment and erosion. For scientists, the escarpment offers a chance to study how ancient rift-related faults influence landscapes long after tectonic motion has stopped. For observers up above in space, it offers a near-perfect example of a continental margin fault. In totality, the Western Ghats Escarpment Fault is more than just a scenic highland, it is a preserved scar from one of Earth's greatest continental separations. With the scale, the clean geometry, and the lasting expression, it qualifies as one of the largest and most visually prominent tectonic cracks on the planet. Number 6. The Karenu Fault, New Zealand. The Karenu Fault, located on the northeastern coast of New Zealand's South Island, became globally recognized after the 2016 Kaikoura earthquake, when it ruptured dramatically across the land, producing one of the clearest visible surface ruptures in modern satellite history. The fault moved over 10 meters horizontally in some places, and it generated a rupture over 30 kilometers long, a scar so clean and visible that it was captured clearly by Sentinel-2 and Planet Labs imagery within a couple of hours of the quake. The 2016 quake was pretty complex. It involved over 20 separate faults rupturing in sequence, but the Karenu Fault was among the most visibly affected. The landscape shows roads, fence lines, and hillsides cleanly sheared and displaced. Satellite and aerial photographs taken immediately after the event show a razor-straight line of brown earth and offset terrain slicing through farmland, roads, and pasture. It contrasts sharply with the surrounding green fields and hills. From above, the rupture appears as a distinct brown scar cutting through New Zealand's eastern coastal plains in a nearly perfect diagonal. It's visible without any enhancement either in moderate resolution imagery, and it stands out in higher resolution platforms, like those used by commercial satellites. The abrupt horizontal shift of terrain on either side of the fault creates a step-like visual pattern, especially where natural or man-made features are visibly offset. The Karenu Fault is part of the broader Marlborough Fault system, which accommodates the motion between the Australia and Pacific plates as the Alpine Fault to the south begins to splay. The fault still is active and under constant surveillance. Satellite radar, interferometry, LiDAR, and repeat photography are used to monitor afterslip and any ongoing deformation. As a modern and very recent rupture, the Karenu Fault is one of the clearest, most dramatic surface cracks currently visible on Earth from space, and it's considered a textbook example of strike-slip fault ruptures for both geologists and satellite analysts. Number 5. The Wadi Araba Fault, Jordan. The Wadi Araba Fault, part of the larger Dead Sea Transformation Fault system, is a linear tectonic crack that cuts through the desert landscapes in southern Jordan, and it is clearly visible from above due to the stark contrast between the terrain on either side. It forms the boundary between the Arabian Plate and the African Plate, and it accommodates lateral motion over millions of years with prominent surface expressions. Running about 160 kilometers from the Dead Sea southwards towards the Gulf of Aqaba, the Wadi Araba Fault is a southern continuation of the Dead Sea fault line. Now, from space it appears like a sharp, straight valley-like feature which dissects Jordanian highlands and desert plains. The crack is so straight that it stands out even in low-resolution imagery, with its path unbroken across large stretches of barren land. The fault creates these offsets, fault scarps, and drainage deflections, and they're all observable in satellite imagery platforms like Google Earth, Sentinel-2, and Landsat-8. One of the most visually distinct segments lies near the town of Garandal, where the fault zone bends slightly and creates an abrupt elevation change on either side. In 1995, the 7.3 earthquake of the Gulf of Aqaba ruptured a southern portion of this fault system, producing a strong surface deformation and permanent offsets. Though no massive rupture has happened recently on the Wadi Araba segment itself, paleoseismic studies show repeated large earthquakes over thousands of years, each leaving behind surface scarps and geomorphic signals that are still visible. From orbit, though, the fault looks like a natural incision in the Earth, enhanced by sunlight casting long shadows along the edge, and the high reflectivity of the exposed bedrock and dry settlement, its remoteness and lack of vegetation allow the structure to remain clearly visible without obstructions. As part of a major tectonic boundary that extends from the Red Sea to Turkey, this fault is one of the clearest examples of a continental strike-slip fault visible from above, and its distinct geometry, rupture traces, and topographic expression make it an ideal inclusion on this list. Number 4. The Shillong Plateau Fracture Zone, Meghalaya, India. In northeastern India, the Shillong Plateau, it's a tectonically uplifted block surrounded by major fault systems that accommodate significant crust motion between the Indian Plate and the Eurasian Plate. One of the most visually striking cracks in this region is associated with the 2001 6.7 Assam quake, which revealed a fracture zone on the plateau's northern boundary near the Dauki Fault. The Shillong Plateau's terrain is marked by sharp linear escarpments that run for tens of kilometers, and these fault scarps are clearly visible in imagery. The Dauki Fault in particular forms a long, dark boundary between the highlands of Meghalaya and the low-lying plains of Bangladesh. It appears in space imagery as nearly a straight tectonic front, up to 300 kilometers long, with abrupt slope breaks, consistent elevation drop-offs, and fault parallel ridges. The Dauki Fault system is not only active but suspected to have produced a massive historical earthquake in 1897, roughly 8.0 on the Richter, which permanently reshaped the plateau's southern edge. From above, the boundary appears as a fault scarp running east-west with tilted strata, folded ridges, and offset drainage basins. The contrast between this uplifted plateau and the flat valley enhance that visibility in orbital imagery. More recent studies using Sentinel-1 radar and Google Earth imagery confirm the persistence of the crack in both morphology and tectonic activity, and while erosion and vegetation have partially smoothed some segments, many areas, especially near the towns of Cherrapunji and Dauki, still show unmistakable linear breaks in topography. This fracture zone is one of India's most geologically significant and visibly traceable tectonic scars, especially due to the distinct boundary between highland and basin. The scale, sharpness, and active nature of it qualify it as one of the best large cracks in the Earth's crust, observable from above. Number 3. The Lake Tanganyika Rift Fault, Tanzania. One of the most geologically striking rift features on Earth lies between Lake Tanganyika, along the border of the Democratic Republic of the Congo, and Tanzania. This isn't really just a lake, it's a surface expression of a deep active tectonic crack, the Tanganyika Rift, a major segment of the western branch of the East African Rift System. This linear fault valley is so large and deep that the lake it formed is the second deepest lake in the world. It goes down over 1,500 meters below the surface. This fault zone is not just visible, it's impossible to miss from space. From orbital imagery including NASA's MODIS, Landsat, and Sentinel-2, Lake Tanganyika appears like a narrow, sharply defined scar that stretches over 650 kilometers, almost perfectly straight along much of its axis. The extreme depth and narrow width are a direct result of the crust pulling apart along a fault boundary. This rift accommodates the separation of the Nubian and Somalian tectonic plates, and over millions of years this tension has stretched the crust and formed a huge depression. The flanks of the lake show dramatic escarpments, some rising more than a kilometer above the surface of the lake, indicating the position of the active fault lines. From above, these escarpments appear as linear mountain walls, while the lake itself acts as a tracer to the rift geometry. Earthquake data does confirm ongoing tectonic activity here, with frequent moderate quakes aligned directly along the lakebed. Recent GPS measurements show divergence between the two shores, while the actual rupture lines lie beneath the lake. The symmetry of the rift flanks, the linear geometry, and the dramatic topography make this a textbook example of an active continental rift that's clearly visible. Sediment plumes and shoreline features also reveal subsidiary fault scarps and smaller parallel cracks along the eastern margins, and in some satellite views, shadowing along the escarpments further enhances the rift appearance, giving it the look of a gaping wound across Central Africa. The Tanganyika Rift Fault is not just one of the world's largest active cracks, it's also one of the clearest and most strikingly straight tectonic features visible from above. Its scale, linearity, and activity make it a critical feature in the story of Earth's ongoing continental breakup. Number 2. The East Rift Zone, Big Island, Hawaii. The East Rift Zone of Hawaii's Big Island is one of the most famous and actively spreading volcanic cracks on Earth, and it's clearly visible from above due to the pronounced features and frequent surface ruptures from lava intrusion and tectonic spreading. Extending southeast from the summit of Kilauea volcano all the way towards the island's coast, the East Rift Zone is a surface-breaking crack system caused by the seaward sliding of the volcano's flank. This movement forms visible rift valleys, tension cracks, and fault escarpments that are easily identifiable from above. This region is, of course, intensively monitored by the USGS, and frequent updates from the Sentinel-2, Landsat 8, and MODIS satellites show fault lines and fissures as evolving surface scars. Major eruptions like the 2018 Lower Puna eruption caused huge cracking along the East Rift Zone, opening dozens of fissures that were clearly visible from orbit. These surface fractures tore through roads, subdivisions, and forests, and they formed a jagged network of parallel rifts and lava channels that remain visible today. The craters and surrounding fissure zones show persistent deformation, especially during periods of increased magma intrusion. But from above, the zone appears like a long, dark ribbon of broken terrain, where cracks align with fissure vents, collapsed lava tubes, and caldera extensions. The contrast between the fresh black basalt and surrounding forested or older lava flows emphasize the rift's outline, and satellite data shows deformation spreading outward on both sides of the rift over time. Unlike continental faults, the East Rift Zone is a volcanic rift system, but it functions similarly with crust being pulled apart along a clear surface trace. But because of its dynamic nature, low vegetation cover, and frequent updates from remote sensing satellites, it remains one of the most visually identifiable tectonic crack systems on the Earth. Number 1. The Baikal Rift Zone in Siberia, Russia. The Baikal Rift Zone is located in southern Siberia. It's one of the most dramatically visible continental rift systems on Earth, and it contains Lake Baikal, the deepest and oldest freshwater lake in the world. Formed by tectonic extension, the Baikal Rift is an active divergent plate boundary where the Amurian plate is slowly pulling away from the Eurasian plate. The result is a massive surface fracture that extends for over 2,000 kilometers, with a core segment running beneath Lake Baikal itself. From space, the rift appears as a long, deep linear depression flanked by steep mountain ranges, and the Baikal and the Primorsky ranges. They make up the unfaulted shoulders of the Rift Valley. The lake itself, nearly 1,700 meters deep, occupies the central graben of the rift, and it acts as a natural visual tracer of the tectonic crack. Instruments like NASA's MODIS, Landsat, and ESA's Sentinel-2 routinely capture detailed imagery of the rift, particularly in winter when snow cover highlights the contrast between the lake basin and the escarpments. The Sarma Fault, Morskaya Fault, and Bargswin Fault, major structures bounding the rift, form sharp, nearly straight lines that slice through the Siberian landscape and are readily identifiable in satellite topography and elevation datasets. The Baikal Rift is seismically active, with regular moderate earthquakes and measurable crust extension between 4 to 5 millimeters per year, as confirmed by GPS measurements. This slow but ongoing divergence is responsible for the lake's great depth and the formation of associated valleys like the Tunka Basin and the North Baikal Depression, which together form a system of aligned surface cracks traceable from orbit. The rift structure also shows a bathymetric fault and scarp beneath the water, but many of these fault scarps emerge on land at the lake's northern and southern tips. These scarps can be seen from satellite images, especially where they intersect with forested terrain and then appear as sudden slope breaks and linear valleys. Because of its enormous scale, clear geometry, tectonic activity, and minimal human modification, the Baikal Rift Zone is not only one of the most prominent surface cracks in Asia, it's one of the largest active continental rifts visible from space anywhere in the world. It is a rare example of tectonic rift at the early stages of continental breakup, caught in high resolution by every modern orbital imaging system.